In today's class, we will look at the noise performance of some simple circuit. Now, before we go there, we need to quickly recap way noise is treated for a complex network. Let us say this is a noisy two-port network, and the input port is port 1 and the output port is port 2. Now, it turns out that this is exactly identical to a noiseless two-port with its noise referred as a noise voltage and a noise current at the input. And I will call those input referred noise sources as En squared and In squared. So, En squared and In squared represent the input referred noise sources of the network. Now, this is unique to the network. So, different circuits will have different values of En and In. The other thing to remember is that in general, En squared and In squared may be correlated. This is because the same set of devices inside the two-port that are producing noise contribute to both En squared and In squared. So, in general you would expect En squared and In squared to be correlated. This correlation may be partial or total, and that really depends on the exact circuit that is being considered. The reason you need both En squared and In squared is because in general this two-port may be excited with any type of source. So, in other words, it could be excited with an ideal voltage source, an ideal current source, or in general a Thevenin equivalent or a Norton equivalent whose resistance might be any particular value. So, to cover the whole range of Thevenin and Norton resistances, you need both En and In to truly represent the input referred noise of the circuit. Now, let us take some simple circuits and try to determine the input referred noise. I will start off with a common source amplifier with a resistive load. Let us say the value of the resistance was R, and at the input I am applying the signal plus some bias, and the output is taken at this point. Now, please note that the input referred noise is a function or is a characteristic of the two-port itself. It should ideally be valid for any value of load resistance and any value of source resistance. So, please note the input referred noise is a function of the two-port itself. So, in other words, the input referred noise should not be a function of Rs or RL. Having said that, we can now say that the input referred noise can be calculated by considering all the noise sources in the circuit. When you are doing noise analysis, the input source does not matter. So, we will ground it. So, the input not a signal of interest. We are only interested in the noise signals inside the circuit. So, I am now going to draw the signal equivalent. This is a resistance R, and the resistance R has a noise current across it. I am going to use this, the Norton or the current source equivalent noise equivalent circuit for the resistor, for a very specific reason which we will see in a minute. So, IRN squared is equal to 4 kT by R times delta F, and it turns out that the transistor also has a noise current which consists of two components. One of them is the thermal noise, which is 4 kT into 2/3 into Gm, times delta f, and the other component is the flicker noise, which is k over WLCox times gm squared by f times delta f. Now we are required to find out the total input referred noise. So in other words, if this were the input, I want to refer all these noise sources back to a set of single noise voltage and current. Now as it turns out, in general a 2-port network would have both an input referred noise current and an input referred noise voltage, but there are several types of circuits which have infinite input impedances. For example, this particular MOSFET has an input impedance that is infinity at very low frequencies, which means that even if there were a noise current, none of it would make its way into the circuit. So in other words, if I were to excite a 2-port with a noise current at its input, and if Zn were infinity, all of this noise current would make its way through the source resistance Rs, and none of it would flow through the input of the 2-port. Therefore, for circuits that have infinite input impedances, the input referred noise source is 0. We will not worry about it. We are only interested in the input referred noise voltage source, in other words En squared or Vn squared. So for this circuit, for the common source amplifier, we are going to calculate this input referred noise. So this is the first circuit that we are looking at. So since the noise equivalent is valid for all values of load resistances, I will say that it is also valid for a load resistance of 0. In other words, the output node is shorted to signal ground. What does this mean for us? Even though it is shorted to ground, I can calculate the output noise current through this short circuit, and if I divide it by the overall transconductance of the 2-port network, in this case the overall transconductance of the amplifier, I should be able to get the input referred noise voltage. In other words, I am going to compare the total noise for this circuit with the following circuit, where both the resistance and the MOSFET are noiseless. If the input referred noise voltage En squared completely represented the noise inside the 2-port, then the output noise current in the two cases should be exactly equal. So let us calculate IN out 1 and IN out 2. So we are saying that the two networks are exactly identical. Let us now calculate these two values. Clearly, IN out 2, IN out squared 1 should be the sum of the noises of the MOSFET and the resistor. And since the noise of the MOSFET and the resistor are completely uncorrelated, I can add the mean squared values at the output. So I am going to add the mean squared values of the noise currents of the two devices, and the point we need to note is that because the output is a short circuit, all of this current will flow through this short circuit. Similarly, all of this current will flow through the short circuit. So, the complete noise from the MOSFET and the resistor will flow through the short circuit because it offers a zero impedance for the current to flow. Now, I will represent the path spectral densities in this fashion. So, that is 4 kT by R plus 8 kT by 3 gm plus the flicker noise. This is the expression for the total output noise current in the first case. What about the second case? I will write that up here. So, the noise current in the second case is nothing but Gm squared times In out squared, because this voltage En squared is going to cause a current through this MOSFET, which is equal to the transconductance times the input gate source voltage. Since we are dealing with mean squared quantities, this noise current squared, mean squared value will be Gm squared times En squared, and because of the short circuit, all of this current will flow through the output short circuit. So, therefore, this noise current in the second case is nothing but Gm squared times En squared. Therefore, En squared is nothing but, or rather En squared over delta F is nothing but 4 kT by R times 1 over Gm squared plus 8 kT by 3 Gm plus K1 over F over WLCox times 1 over F. This is the noise, total noise path spectral density at the output for this particular circuit, and we divided that by the square of the transconductance to get the input referred noise voltage source En squared. So, now I hope you can see that you can follow this method for any given circuit. We will do a couple of more examples in today's class. Now, the point to note is there are two significant points to note. First of all, for this particular amplifier, the input impedance was infinite, and therefore, we stopped with calculating only the input referred noise voltage. But there are MOSFET circuits where the input impedance is not infinite, and therefore, we would have to calculate the input referred noise current also. We would follow the exact same procedure where we would apply an input referred noise current here, and we would calculate the overall output noise current when we apply this input referred source, and then we would calculate the overall short circuit current without this source when the resistor and the device are noisy. We would compare the two cases and we would determine the value of the input referred noise. More importantly, I have considered a short circuit at the output because the MOSFET being a voltage controlled current source element, it is often very easy to think in terms of the device currents, and we know that currents tend to take the path of least resistance or least impedance. Therefore, if we short circuit the output, we know that all of the current will flow through that output node, and therefore, the analysis simply becomes easier. It is perfectly fine to consider the output node as an open circuit and find out the output referred noise voltage and divide it by the overall voltage gain of the circuit. In other words, you find out the output referred noise voltage in both cases with and without En, and you equate the two and determine the value of En squared. You may rest assured that you will get the exact same value in both cases. Let us try one more example. I will take the same common source amplifier, but now I am going to use an active load, in other words an active PMOS load instead of a resistor. So, let us say this transistor was M1 and the PMOS transistor was M2. I want to find out the input referred noise voltage for this circuit, and clearly because the input impedance is very high, the input referred noise current is irrelevant for this circuit. I will follow the exact same procedure to do this example also. I will first note that both these transistors have drain thermal noises. Please note that when you are considering noise, especially when the noise sources are uncorrelated, the direction of the noise current does not matter, because you are always adding them in mean squared terms. And I have two drain thermal noises. I will denote them by ID N1 squared and ID N2 squared. For this particular example, I will ignore flicker noise, but please note that it is very easy. The behavior of the circuit for flicker noise is almost exactly the same as that for thermal noise. The only difference is that flicker noise is frequency dependent, whereas the thermal noise is not, it is white noise. I am going to short circuit the output, and I am going to calculate IN out 1 squared. Clearly, this is equal to ID N1 squared plus ID N2 squared, because both of those noise currents will prefer to flow into the absolute short circuit at the output node. Because the two noise sources are uncorrelated, I can add them as mean squared quantities, and therefore the total output noise current in this case is 8 kT by 3 into GM1 plus GM2 times delta F. Now, I consider the other case when both these transistors are noiseless. And I only have the input referred noise source En squared at the input, and please note that noise is a small signal. So, all small signal quantities, all small signal analysis is valid for noise. And in this case, In squared 2 is nothing but GM1 squared times En squared. Now, I know that this should be equal to In out 1 squared, and therefore En squared by delta F is simply 1 over GM1 squared times 8 kT by 3 into GM1 plus GM2. So, this is the input referred noise voltage squared for this particular circuit. Now, let us look at this in a little bit more detail, because this is quite interesting. So, I will write it again on this page for your reference, and now I am going to take the GM squared inside the braces. So, I obtain 8 kT by 3 into 1 over GM1 plus GM2 over GM1 squared. Now, clearly for an ideal noiseless 2 port, En squared would be 0, In squared would be 0. So, if I want to reduce noise, we want minimum En squared and In squared. In other words, if you are trying to create a circuit that is not very noisy, you want to minimize the magnitude of En squared and In squared. So, let us apply that philosophy to this particular circuit, which is the common source amplifier with an active PMOS load. Let us say we want to minimize En squared. What design implication does it have for us? So, this means clearly Boltzmann's constant and the temperature of operation are not under our control in a majority of cases, but there are some cases where the temperature might be under our control, because if you want a really low noise circuit, you might need to cool down the ambient temperature of the circuit, and there are some cases where this is done. But in the majority of cases, you do not have control over the ambient temperature, and therefore, the only design parameters, as you can see, are GM1 and GM2. In our case, this clearly points out that we need to maximize GM1 and minimize GM2. Now, please note that the gain of the circuit is a function of GM1, and therefore, for a high gain amplifier, you do have some control over GM1, because now the gain of this particular circuit, for example, is minus GM1 into RDS1 parallel RDS2. The gain of this actively loaded common source amplifier is minus GM1 into RDS1 parallel RDS2, and there is some, by choosing a particular value of RDS1 and RDS2, there is some design freedom for choosing the value of GM1 for a given gain. Now, what this tells us is you have to maximize the value of GM1. Now, let us go back here to the circuit, and I wanted to point out that this may seem a little bit counterintuitive. If you maximize GM1, you are actually maximizing this noise current. In other words, the noise current flowing through the output is increasing. So, it may seem, at least at the beginning, on the face of it, it seems a little bit counterintuitive, but please note that the noise current squared increases linearly with GM, but the output signal increases as the square of GM. In other words, In out squared from M1 is proportional to GM1, but this is the output signal is clearly, the output current is clearly Gm times Vs, which is the input signal, and if you are looking at I out squared, which is the output current power, this is proportional to Gm1 squared. So, if you choose a larger Gm1, you will get a larger noise, but you will get a much larger signal. So, you will get larger gain, RDS1 and RDS2 being constant. If you choose a larger Gm1, the gain will be even larger, and therefore, the signal to noise ratio at the output increases with Gm. Please note this. What about Gm2? In this case, because Gm2, the PMOS transistor is being used as an amplifier, is being used as a current source, and therefore, it contributes no signal gain, but it only contributes noise. Therefore, we want to, if you make Gm2 larger and larger, the second current source keeps getting larger and larger, but the signal power does not increase with Gm2, and therefore, you do lose on signal to noise ratio. Therefore, for a low noise circuit, you want to minimize Gm2. What does minimize Gm2 mean? Please note that the current through the circuit is some bias current I naught, which is the same for both circuits, for both transistors, and has been chosen, this bias current I naught has been chosen such that the transistors have a certain W over L and a certain Gm. Now, let us assume that you are trying to keep I naught constant because you do not want to tamper with Gm1, which you have chosen in a particular way for noise. For constant I naught, if you want to minimize Gm2, this can be done only by minimizing W over L of M2, which is the PMOS transistor in this case. Now, if you keep the bias current constant and try decreasing W over L, what happens is the VD sat or the VSD sat of the PMOS transistor in this particular case, it is the source gate voltage minus VTP. Please note that this is inversely related to the W over L of the device. In other words, if you have a constant VB2 at this point, you are for a constant current, by minimizing Gm2 and therefore minimizing the width over length, you are compromising the minimum voltage required across the transistor M2, the minimum voltage required to keep the transistor in saturation, and that is extremely important to get large gain from this circuit. So, if you try to decrease VD sat of the PMOS transistor increases and swing limits of this particular amplifier decrease. So, clearly there is a trade off between noise performance of the circuit and the swing limits of the circuit. And this is a classic trade-off in analog circuits, because as processes scale, as IC processes are moving from longer channel length technologies to shorter channel length technologies, you find that the power supply scales, and for the same noise your overall dynamic range is being constrained, because on the upper side, as the power supply voltage decreases, you are constraining the voltage, and therefore there is a certain limit SNR limit that is being imposed upon by this process scaling. Now let us look at a slightly different variant of this circuit. I am going to look at the cascode amplifier. Let us take the resistively loaded, because that will give us one more noise source. So let us say I have M1, I have M2 and I have a resistance R, and I have a bias voltage VB1 plus the signal applied here at the gate of M1, and I have some bias voltage VB2 at the gate of M2. And now I want to find out the input referred noise voltage of this particular circuit, and as before I am going to short circuit the output. Look at the output short circuit noise current squared. There are 3 noise sources for this circuit. IN1 squared, IN2 squared and IRN squared. Now these 3 noise sources are completely uncorrelated, and I will need to find out the output component of the noise from all 3 of them. So in fact I will write down the 3 components here. Now we need a small change in notation. So let us say that the output noise due to M1 is INM1 squared, and the output noise due to M2 is INM2 squared. So these are the 3 components flowing through the output. Please note that the noise from the resistor flows directly into the short circuit. So that is why I have written it straight away at the output. Now we need to calculate the component of noise current IN1 that is flowing through the output, and I am going to call that INM1, and I need to find out the component of IN2 flowing through the output, and that I have called INM2 squared. Let us calculate these 2 quantities. So to do that, I will consider each one in turn. So I am interested in the noise current flowing through the output short circuit due to IN1 squared So now at the drain of M1, clearly the noise current has 2 paths to flow. One is back into the transistor, the other is into M2. So to understand this a little bit further, we will need to draw the small signal equivalent circuit. I will call this intermediate node voltage as Vx, and therefore, this current source for M2 is minus GM2 times Vx, because the gate is a small signal ground. Please note that for noise purposes the gate of M1 is also grounded, and therefore, this is GM1 times 0, and at this point I am applying the drain thermal noise of M1, which is IDN1 squared. Now, this current has to flow in only one of two paths. It either flows through RDS1 or it flows up here. Now, it turns out that the impedance looking up is simply 1 over GM2, because this current source comes completely in parallel with RDS2. This current source is, please note that the direction of the current source can be changed, and if you are trying to find out Z up, this is purely 1 over GM2, and that is of course in parallel with RDS2. The impedance looking downwards is RDS1, and as you can see clearly, for typical values of GM and RDS, Z down would normally be much larger than Z up, because Z up is approximately 1 over GM2, whereas Z down is RDS1, and therefore Z down is much larger than Z up, and we can say that almost all of this current will make its way to the output. So, in other words, most of this current, almost all of this current will flow up into M2 and eventually into the output. This means that IN M1 squared that we have been trying to calculate is simply IN1 squared or IDN1 squared which is 8 kT by 3 GM1 times delta F. What about ID2? Now, let us take that circuit. Now, for this particular case, both the gates of M1 and M2 are grounded, and I am now looking at a current source between two nodes. Now, to analyze this circuit, we will use a small network analysis technique. So, if I have a current source I1, as far as the rest of the networks across A and B are concerned, this is exactly the same as putting two current sources in series, whose value is exactly the same. There will be no violation of either KVL or KCL if this is done. Number 2, even if I decide to ground or apply any specific voltage at the intermediate node, please note that there is no current through this node. You can clearly see that by applying KCL at this intermediate node, and therefore the rest of the network is not disturbed across it. This configuration looks exactly the same as this configuration across the nodes A and B, and we will use this particular technique to analyze the circuit. So, we will split IN2 squared as two sets of sources. To do this, I will make a copy of this particular network. I will show this in blue. I am maintaining the same direction, and I am going to short the intermediate point to incremental ground. As you can see, now it is, the network looks a little bit more complex, but it is actually easier to analyze. I am going to call these two sources as Ix squared, and of course this are both, and I am going to call them Iy squared to distinguish the two, but in reality both of these are equal to In2 squared. Now it is very important to note that Ix and Iy are completely correlated. So in other words, since we are splitting the same In2 squared into two current sources in series, these two noise sources Ix and Iy are completely correlated. What this means is, whenever you hear the word correlation with respect to noise, you need to keep track of signs of the noise voltages and currents. In this case, we need to keep track of current directions. So, we are, to summarize, we are trying to calculate IN_M2 squared. So, IN_M2 squared will have two components, one from Ix, the other from Iy. So, the first component from Ix will clearly be equal to Ix itself. In other words, the current source Ix has the option of flowing back into M2 or flowing out of flowing into the short circuit. Since current always takes the least resistance path, all of Ix will flow into the output short circuit. What about Iy? If you look at Iy, it has the option of flowing into the lower path which has a resistance RDS1 or the upper path which has a resistance 1 over GM2, and therefore most of this current Iy would normally flow through the transistor M2 and eventually flow into the output node. The only thing we have to be careful is to keep track of directions. Now I notice that I have used different directions, let me please correct them. So since I have taken a specific direction, this current, the current flow path for Ix is downwards and the path for Iy is upwards. I will show that in a different color like this. So therefore, now we no longer deal with mean squared quantities because we have to keep track of correlations, and therefore we have to talk about the signal with the signs involved. So, In M2 will have a component from Ix which is Ix itself, minus, please note that the two current directions are opposite, minus Iy, because almost all of Iy flows through the output also in the opposite direction. This means that most of the noise from M2 does not make its way to the output. And therefore, now we can write the total noise current at the output, which is 4 kT by R plus 8 kT by 3 GM1. In the case where I have a noiseless circuit with an input referred noise, we know that the overall transconductance of the cascodes is the same as that of the device M1, and therefore In out 2 squared is GM1 squared times En squared, and therefore En squared by delta F is nothing but four kT by R into 1 over Gm squared plus as you can clearly see, the noise from the cascode is appearing at the output. In other words, appearing in the input referred noise source is very small. The cascode increases the output impedance, but it contributes very little noise to the output, especially at low frequencies.